Hello. Question 3, cantilever beam support post problem. Essentially what we're looking at is a support post which is restrained at the top and bottom and is held at the bottom vertically, and the flexure in the posts is causing additional deflection in the beam. The floor heights are equal, they're given as 2.5 meters, and the applied load is 5 kilonewtons, and the cantilever is 1.5 meters. So the timber post and beam, which are in glulam, which is a form of timber, the sizes are given in millimeters, and the I values, which can be readily calculated, are also given. Long-term and short-term moduli are given for two different purposes. The long-term modulus may be calculated as the short-term modulus divided by 1.6. Question 3a. What we're going to do is we're going to fix up the support for the post for the beam as if the post isn't there. So we're going to look at it as a pure cantilever problem with 5 kilonewtons and 1.5 meter cantilever. The deflection may be found from PL cubed over 3EI for the beam from figure 2.3.2. Putting in the numbers with consistent units, we come with using the long-term modulus, which allows a creep, we come to a value of 7 millimeters deflection. This is purely from the flexure of the beam. Question 3a continued. We're going to look at the deformed shape of the post, which helps us visualize the bending moment diagram. So the deflected shape, we're going to look at the flexure in the beam, which gives tension on the top. It rotates clockwise and then it deforms the post into an S-shaped curve, and the bending moment is PL, which is a pure cantilever bending moment with tension in the top, and the posts split into half this moment and 0 at the supports, given that the post is the same height for the ground floor and the first floor. Question 3b, and now we're going to look at the effect of the tip deflection in the beam from the deformation in the post. So from chapter 2.9, page 105, rotation is ML over 3EI, where M equals PL, and M is the top of the lower post. M over 2 is PL over 2, and the deformation in the rotation comes from in the post, which it comes out at PLH over 6EI, resolving the equation. The rotation is 0.013 rads, and the deflection comes out as this times the cantilever distance, which is 19.5 millimeters. Question 3c. We summate the deflections from both cases, from the flexure and the rotation of the post, giving us 26.5 millimeters. 7 plus 19.5. As a span over deflection ratio, this comes out to 57, which is low. And for the natural frequency, we use a short-term modulus. So what we're going to do is we're going to prorata this value from the long-term to the short-term modulus, and this gives 16.6 millimeters from chapter 212, page 132. The approximate natural frequency is a ratio of 15.8 over that deflection, which gives about 4 Hertz. Again, we're assuming that the load is somewhere near dead load plus 10% of live load. Question 3D. We're going to increase the post to 270 in depth, and the I value comes out PD cubed over 12, which comes out as 22963 centimeters to the 4. Working out the deflection due to the rotation, we prorata from 3B, so we took 3201 from 3B, we come out at 3 millimeters. So we now summate them with the deflection of the beam, deflection and the post, which will give us a natural frequency using the short-term modulus. We prorata that at 6 millimeters, so the natural frequency is 15.8 over root 6, which is 6.5 Hertz. This is less than 8 Hertz, which is possibly what we really want, so it may take further consideration, but at this stage it seems reasonable. Thank you for your time.